Hello, welcome to this video. Today we're gonna look at a nice problem of light bulbs in a circular room. So let's say you have a room in the shape of a perfect circle, and on the room's walls, equally spaced from each other, are these light bulbs. And let's say for now there are n light bulbs. And now, and the radius is given, and the radius of the room is given as r. Now let's say you are standing somewhere in the room, a distance d away from the origin. What we want to find is as the number of light bulbs grows to infinity, or let's say you have a bunch of light bulbs in the room, a huge amount, what amount of the light is what amount of the light are you gonna see? So how much light are you gonna see through your eyes? How much will you perceive? And so, but if I say that the light bulbs continue to be the same as I put more an infinite amount around the room, the amount of light in the room will obviously grow to infinity, because it's gonna be it's gonna be some non-zero amount for each light bulb, but we add infinitely many of them, they'll grow to infinity. So what we're gonna do is say the more light bulbs we add, the lower their quality is, by saying that, so first of all, if you're a distance x from a light bulb, the amount of light you perceive is proportional to 1 over the distance squared. So it's going to be 1 over x squared when it's proportional, so it's times some constant. And as n grows to infinity, we want to divide that constant by something to balance the enormous amount of light bulbs we'll have, and we'll do that by having a completely fixed constant c over n. And actually, let's say c is just 1, because c is multiplied by everything, so at the end we'll have c times something, and we're not interested in c, we're interested by what c is multiplied by. So we're going to say times 1 over n. So this is just the strength, and this is the amount of light you perceive, a distance x from a light bulb. And now we're gonna calculate how much light you perceive as the number of light bulbs grow. So what we're gonna do is transform this into a coordinate system. So we're gonna say this is 0, 0, this is the x-axis, this is the y-axis, and I'm picking the x-axis so that we are on the point d0, because we're on the point d0, and because we're going to have the number of light bulbs grow to infinity, I'm just going to say that there's a light bulb here directly on the intersection of the x-axis and the circle, and then from there I grow them out. I add more and more when they're equidistant from each other. So I'm gonna look at the kth light bulb. So let's say it's this one. The angle it will make, so because we have a total of n points, and they're going around the circle, they all make an angle of 2 pi. Meaning that if I pick 2 any 2 points. So let's say this angle will have to be 2 pi over n, because symmetrically it's all the same around the circle. But if I want to look at the kth light bulb counterclockwise from the one that sits on the x-axis, I'll have to add k. I'll have to add k of these angles. And I also have to mention, by kth light bulb, I mean this is the 0th light bulb, this is the first, second, and let's say, and this is third, and so on. The kth light, and then we need to add 2 pi over n. K times to get the angle it makes with the x-axis. So the angle will be 2 pi k over n. So this is theta. Theta is 2 pi k over n. And now, because it's on a circle with a radius r, I can say, I'll leave it for you to understand why, but it's all it is just completing this triangle here. You see that the coordinates of the kth light bulb are cosine theta, which is 2 pi k over n, r sine theta, or 2 pi k over n. This is the kth light bulb. And now that means that we can, and because we know the coordinates of us and the kth light bulb, we now know the distance of between us and any light bulb we pick up in the room, and it's going to be by Pythagoras, that distance, which I'll call xk. If I square it by Pythagoras, it is, I'll let you check for yourself why it's by Pythagoras, but here, instead of completing this triangle, you're completing this triangle, and you know this length and this length, and from that by Pythagoras, 2 pi k over n minus d squared plus r sine 2 pi k over n squared. This is the distance from the kth light bulb. And now let's expand these out and simplify a bit. So this is r squared cosine squared 2 pi k over n minus 2rd cosine 2 pi k over n plus d squared. This is this, and this is r squared sine squared of 2 pi k over n. Okay. Now, we do have things to simplify here. One thing actually, we have sine squared plus cosine squared, and we know that that is equal to 1. Meaning that this is just, this plus this is r squared, if we factor r squared out, plus d squared minus 2rd cosine 2 pi k over n. Okay, now this is how much we can simplify this. Now we will use this to find the amount of light we're getting from the kth light bulb, and then we'll sum it all, and then we'll sum it all over the light bulbs. So I'll call it, so because it's light, I'll call it L, and LK, this is gonna be, now 1 over the distance squared times 1 over n, and the distance squared is just this. This is r squared plus d squared minus 2rd cosine 2 pi k over n. Alright. Now, now we figured this out. Now, like I said, we're just going to sum from all over the light bulbs to get that the total light, which will write as L, will be the sum as K goes from, well, I said we're starting at the 0th light bulb. We call this one the 0th light bulb, the one that's on the x-axis. So K starts at 0, and because we need to have n light bulbs, we need to end at n minus 1. 1 over n times 1 over. Alright. But now remember, we want the number of light bulbs to go to infinity. And if the number of light bulbs grows to infinity, what we have here is precisely a Riemann sum that describes an integral. And it starts at 0, ends at 1, and here we have our 1 over n of some function of our xi, which in this case is k over n. And here we have it in our cosine. And so if you think about it a bit, as n goes to infinity, you'll see that by definition, this is the integral from 0 to 1 of 1 over r squared plus d squared minus 2rd cosine 2 pi x. This is just dx. Okay, now let's clear this and we'll figure this integral out. Okay, let's begin going at this integral. So first thing I'm gonna do is cosine 2 pi x is not that fun to work with. It can be a bit annoying. It's much more fun to just work with cosine x, or for reasons you'll see shortly, I want this to be cosine 2x. So I'm gonna do a u substitution to be pi x, and so du is pi dx, and dx is du over pi, meaning that I'll have to divide by pi here. And so this is the integral. Now, it started at 0 and ended at 1, and we're just multiplying by pi. So this is going from 0 to pi. Now, dx turns into du over pi, so I'll put the 1 pi out of the integral, and I'm left with du over r squared plus d squared minus 2rd cosine 2u. Now I'll split cosine 2u by the formula by the double angle theorem for cosine, which says cosine 2 theta, right here, cosine 2 theta is equal to 2 cosine squared theta minus 1. Now for reasons, okay, now again, I have this. Now, for reasons that will seem so this will now seem to be out of nowhere and unnecessary, but you'll later see later see why this was needed, but I'll now make another substitution. V is u minus pi over 2. So dv is just du, meaning that this is 1 over pi times the integral from, it's not going from 0 to minus pi over 2, so it's going from negative pi over 2 to pi over 2 of dv over r squared plus d squared. Now, v is u minus pi over 2, and so u is v plus pi over 2, and so 2u is 2v plus pi, and so cosine of 2u is negative cosine of 2v, and meaning that this negative turns into a positive, so this is plus 2rd cosine 2v. And now I will use this formula to get that, to turn this into just a cosine v, because cosine squared v will be nicer to work with here. This is 1 over pi, the integral of negative, from negative pi over 2 to pi over 2 of dv over r squared plus d squared. Now, this is going to be, from this negative 1, minus 2rd, and then from this 2 cosine squared, I'll get plus 4rd cosine squared v. And now, so I'll do two things. I'll pair up this to get r minus d at all squared. But what I'll also do is divide by cosine squared v on top and bottom. And you'll see why this is useful. And this is 1 over pi, the integral from negative pi over 2 to pi over 2. Now, on top, we'll get 1 over cosine squared v, or secant squared v. And on the bottom, we get r minus d squared, which is this, times secant squared v. And plus 4rd dv. Now notice that up top, secant squared v is exactly the derivative of tangent v. And so, to make for a nice substitution, I'll make the secant squared v on the bottom, tangent squared v plus 1. And I'll get 1 over pi, the integral of negative pi over 2 to pi over 2 of secant squared v over r minus d squared tangent squared v. Now, the plus 1 turns into plus r minus d squared, and then plus 4rd will turn into r plus d all squared. And I'll let you check for yourself why this is true. And dv, now I'll make the substitution of t equaling tangent v. And now notice, this is why I changed the bounds from 0 to pi to negative pi over 2 to pi over 2. Because if I would have kept it 0 to pi, I would have had tangent 0 to tangent pi, which is 0 to 0, and would have had the integral would be 0, even though clearly by our problem the light we perceive has to be bigger than 0, which would make it a completely wrong substitution. But now, negative pi over 2 to pi over 2, the tangent of each one of them is not the same, and so we can do the substitution. And now here, dt is secant squared v dv, and this is going to equal 1 over pi times the integral. Now, tangent negative pi over 2 is negative infinity. Tangent of plus pi over 2 is plus infinity. And now we'll get dt divided by r minus d squared. T squared plus r plus d squared. Okay. Now, this looks a lot like the derivative of arctangent of t, which is 1 over t squared plus 1. We just have to modify things a bit here. So what I will do is divide on top, on numerator and denominator, by r plus d squared. And then on the top, I'll get 1 over r plus d squared, which I'll take out of the integral. So you get 1 over pi r plus d squared times the integral from negative infinity to infinity of dt divided by t times r minus d over r plus d squared plus 1. Now I will make yet another substitution, and so we'll say, but this will be our final substitution. I'll say y is t times r minus d over r plus d, and I'll get that this is, and so dy, no, I'm not going to write that, but dy is dt times this thing, and so we need to divide by this, take the reciprocal, and then that will be, and then dt times 1 over this will be dy, and because it's a constant, I'll just take it out of the integral, so r plus d over r minus d, and then times 1 over pi times r plus d squared. I'll let you look a bit through that, but you should get 1 over pi times parentheses r squared minus d squared times, now this is positive because I'm saying the distance d is smaller than r because we're inside the room, meaning that, and so r minus d is positive, r plus d is obviously positive, so this is a positive constant, meaning that the integral still goes negative infinity to infinity, and I will have dy over y squared minus 1. This is precisely now the derivative of arctangent y, this thing inside, and so the integral of this will just be arctangent y. And so this will be, and this will be 1 over pi r squared minus d squared times arctangent of y, going from negative infinity to infinity. Now arctangent of infinity is pi over 2, arctangent of negative infinity is negative pi over 2, pi over 2 minus pi over 2 is pi, and so this integral evaluates to pi. Now pi cancels with pi, and we'll get our final answer. Very simple answer. 1 over r squared minus d squared. And considering the simplicity of the answer, there is probably an easy way to maybe geometrically look at this and eventually get just one light bulb that we perceive 1 over r squared minus d squared from it. But regardless, that is our final solution. And if you want to, you can look at the graph of this function and see how much the amount of light you perceive changes as you move around the room. But that does not matter to us anymore because we solved the problem. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. Finally, that's it, and Happy New Year!